Yes. Okay. Thank you. Yes. Okay. All right. Well, don't look at me. Hey, look at everybody else. All right. Pepper is hoping you guys study hard and do well on this upcoming test that we've got. I'm a little out of breath because just chasing the puppy around. But here she is by request because it was like on the survey. Anyway, she came up a few times on the survey. So I'm going to put her aside because she's a little distracting and heavy. And I'll be right back. Go, girl. Yeah. All right. Okay. Go, girl. All right. Feel a little bad because she thought I wanted to play, which I kind of did. But we're going to play physics. It's almost as fun as playing with a puppy. All right. So, good evening. Happy Sunday. We've got our test on Tuesday in this for momentum and impulse. It'll be the last unit test we take of 2021. It'll be the last unit test we take for this semester. There are 2 standards. Each standard, just like all the others, will be 50 points each, summative. And so, yeah, I mean, it's pretty straightforward. So I want to get straight to it. And there were a few questions that came up in the survey. So hopefully I could answer them. And if you're not sure about what I'm going to ask, well, at the top of the this right here, it'll be, you'll see what I'm talking about. So like it says on there, be ready to take some notes, like pay attention to this, like kind of be engaged here, watching just this, don't try to do something else at the same time. It doesn't work that way. You actually have to like give 100%, the more you give, the more you're going to get out of this, and the more you'll be prepared, and hopefully the better you'll do on this test. So, and tests to come, because we have another test, and I'll talk about that in class, the final exam coming up a week later, week from tomorrow, basically. So yeah, and if you've got questions, you could chat here just like usual, or on Remind. I will get you on my phone over here off to the side. There was something else I was going to say. So, oh yeah, just some general tips, I guess, on this unit. And in physics, keep in mind that the language of physics, the conceptual stuff is important. Understanding the concepts is important, but the language of physics is math. And so when you are stuck on something, or if you need to think of something, try to think in terms of the equations. So if I put those up here, I don't give you the equation sheet, it's not just like, this is not a side to physics. This is how we describe the physics. So the impulsive momentum is right on the front middle, impulsive momentum. There's a little box right here. And, be familiar with what all the letters mean. Most of them we've used for a while now. And just making sure the stream looks good. All right, cool. And just be aware of what all these letters mean. So let me zoom in just a little bit here. Impulsive momentum. So obviously P is momentum. If you don't know that, then you have a lot of catching up to do. But remember, what is momentum? It's mass and velocity. So this is not just an equation just because you got to do some math. Like this, like I said, math is the language of physics. Physics uses math to describe what's going on. So that's what I'm saying. Like, so what is momentum? It's mass and velocity. Mass times velocity. It's both together. What is impulse? Impulse is not a word that comes up a lot outside of a physics class in Star Trek. And so what is it? It's force times time. It's a force along with a time. It's that whole hit hard and follow through when you're hitting something with a bat or a golf club or something like that, or you're kicking. You got to kick hard, follow through. You got to. It's also the opposite. If you want to reduce the force on something, an impulse is a change here. An impulse is a change in momentum. An impulse causes a change in momentum. And so if you're stopping a ball or a water balloon or an egg or anything that's got momentum, that's moving, you have to apply an impulse. Driving a car, you have to apply an impulse to get the car going by pressing the gas. And just like with anything else, if you apply a lot of force, you're going to not require a lot of time to accelerate, but everybody in the car will notice because you're applying a lot of force. And same thing, if you accelerate really slowly, you take a lot of time to accelerate, it's going to be nice and easy for everybody, and you're not going to feel a lot of force. But because there's not a lot of force, you won't accelerate as much. And all these math concepts all come together. And then when you are stopping the car or catching the egg or the ball or whatever, it's the same thing, but in reverse. You have to take away that momentum. You have to take a negative momentum, apply a negative impulse. You have to apply a force in the opposite direction to slow it down and stop it. And like in a car, if you apply a lot of force, it's not going to take a lot of time to stop, but everybody will feel it. Or if you do a more normal controlled stop, it'll take more time, but less force will be involved. If you hit a brick wall, it's not going to take hardly any time at all, but there's going to be all sorts of horrible forces involved. You get the idea. Like, use these equations to think through the concepts. Don't just think of them as something I have to use for the math questions. All these are related to each other. Impulse is force times time. It's this equation right here, except they're separate. Any of these four things can be related to each other. They're equal to each other. So a force and a time, aka an impulse, will cause a mass to change velocity. Whether it's to speed up or slow down, that depends on what's going on. And so a change in velocity for a mass is called a change in impulse, or change in momentum, which is caused by an equal impulse. So all these concepts that we've been talking about in class for the last week or two or three are encapsulated in these equations because, well, this is the language of physics. So if you're ever stuck, is my point, or you just need to kind of put it all together in your brain, check out the equations. And then the whole thing about the total momentum before and total momentum after, that whole chart setup that I showed you, it's just taken this idea. This is the idea of conservation of momentum, and it's just right there. That right there is everything we did over the last several days. So all right, cool. Well, let's take a look at some specific things, specific questions I have for you. Let's see if I'm drawing. Where's my little cursor? There it is. All right, cool. So I guess I'll do the thing again with maybe I will. Let's see. Let's say you gotta do this every time though. That's the problem, is it takes a little while longer, and we'll try it though. We'll see what happens. So why does the egg break when it hits a wall, but not when it hits a sheet? All right, so that's going to be an important question, and we'll see how this goes. And I might not do the poll thing every single time. We'll see. Is it because A, the wall is hard, so it doesn't absorb the impact like the sheet does? Is it B, the wall naturally breaks the hard eggshell? C, the wall stops it in very little time, so more force acts on the egg? Or is it D, the momentum is changed too much when it hits the wall? I'm not seeing a ton of interaction today, so I just might forego that a little bit. Let's see. I guess I'll end the poll right now. All right. Well, yeah. All right. I don't think I'm going to do the poll very much. Did I just end it? Yeah, I think I might have deleted it. All right. Oh, there we go. Okay, cool. A and B were the choices with 2 votes. All right. Let's take a look at those a little bit. The wall is hard, so it doesn't absorb the impact like the sheet does. All right. We got to get away from using this word absorb, because it absorbs the energy, but we haven't talked about energy yet. We're going to talk about energy next semester. Because we use the word absorb, and I mean, to be honest, it doesn't mean necessarily, it's not describing what we think it's describing, because it doesn't absorb it. Everything absorbs the energy. It's just how quickly it absorbs the energy or releases the energy. It's not about absorbing. So if you see the word absorb, it's a trap. Don't answer it with the absorb question or absorb choice, because it's, like I said, it's like the the trick. It's not even the trick. It's just like we naturally fall onto explain it. It looks like the sheet over in this little picture here is absorbing the impact. But what does that mean? And that's the important part, is to explain what that means. Okay, so it's not going to be A. The hard wall naturally breaks the hard eggshell. Well, yes, it does. But why? Why? That naturally, okay, we're trying to understand the nature behind this. So the question is why? The wall stops in a very little time, so more force acts on the egg. That is the winner right there. That has to do with that whole, okay, the whole idea of impulse is force times time. Just remember, the egg is going to stop. Whether it hits the sheet or the wall, it's going to stop. And when it stops, that means it's losing momentum. And losing momentum means that something took the momentum away. And we take momentum away, or at it, by applying an impulse. So that sheet or the wall is applying an impulse. That's the definition of impulse. And so the sheet gives more time, which means that less force is required. It's like stopping a car. And the momentum has changed too much. Okay, so that is just not true, because both times it's going to be the same exact change in momentum. The egg is flying through the air. It has a certain amount of momentum, and whether it hits the sheet or it hits the wall, it's going to have the same change in momentum. Okay, and that change in momentum is caused by that impulse. Impulse causes a change in momentum, and that is that force times time. And once again, if you can increase the amount of time it takes to change the momentum to stop the egg, then you have less force. All right. All right. Ask questions. You could again put it in the chat or send it to Remind. I'm going to move along. What has more momentum, an apple thrown at 10 meters per second or a bowling ball thrown at 10 meters per second? And let's see what's going on here. I think I'm going to just kind of not do the poll for now. We'll see what happens. So just think it through a second. More momentum, an apple thrown at 10 meters per second or a bowling ball thrown at 10 meters per second. The apple because the apple because P equals mv, the apple because it has less mass, the bowling ball because it's moving faster, or the bowling ball because it has more mass. All right, well, this is true. Let's see if I can tilt this. Maybe my line's a little straighter. This is true. Momentum is mass times velocity. And remember what I said at the beginning is use these equations to think through the concepts. Okay, the question is which one has more momentum, which means more. All right. Well, we got both choices here, but we want to know which one has more momentum. And it's mass times velocity. Well, both of them have the same velocity. And so what we have to look at to see which one has more momentum is which one has more mass. All right. And so the answer is, yeah, D, because it's not moving faster. It's moving at the same speed. The apple because it has less mass. Well, that's just not true because of what I just said here. The apple because it has less mass. No, it's the opposite. So you guys who both said less mass or weighs less, it has more, which is more. Okay, and like I said, use the equations to think it through, to guide your thinking in this. It's not meant to be a trick question, so just make sure that your thinking is straight here. More momentum means a bigger combination of mass and velocity. And since both have the same velocity, you got to look at which one has more mass. All right. All right. But this is true. Less mass does make it easier to move. You're absolutely right. So to throw an apple at 10 meters per second is going to be way easier than throwing a bowling ball at 10 meters per second. And if you think about that, you have to apply much less of an impulse on the apple to get it to go 10 meters per second. And if you have to apply much less of an impulse on the apple, well, impulse is equal to the change in momentum. So if you have to apply a smaller impulse on the apple, that means it's going to have a smaller momentum. All right, remember, these equations are meant to guide you on this stuff. So you're absolutely right. It's easier to move, which means it has, and the bottom line is they're both going 10 meters per second. They both have the same velocity. They both have the same velocity. And to get the bowling ball going that fast would take a lot more effort, a lot more impulse. And since it took a lot more impulse, the bowling ball has a lot more momentum. If you think about the opposite, which one's going to take more impulse to stop? I would much rather have an apple coming at me at 10 meters a second than a bowling ball coming at me at 10 meters a second, because it's going to take a lot less effort, a lot less impulse to stop the apple because it has less momentum. All right. Keep those comments coming. That's good. I mean, these are good questions and good statements you guys are making here. So it helps me understand where you're coming from at this, because I mean, I gotta understand. I have ideas about common misconceptions, but I don't know what your specific. Hi, Perry. I don't know what your specific misconceptions might be. And if you say this stuff, it'll help me. And don't be afraid to put that in there, because I mean, we're all human. We're all going to make mistakes. And if you knew all this stuff coming into it, you wouldn't need to be in this class. You could be teaching it like me. I had to learn it at some point too. I probably had to learn it a few times. So don't worry about sounding foolish or anything, because you don't. It's definitely way more foolish to sit there and quietly fail than to, hopefully that didn't mean anything, than to ask a question. All right, I heard dun, so I'm guessing everything is good. All right. Variables to represent the following. Make sure these are rock solid in your thinking. I did not ask these on the review guide, I don't think, but definitely make sure that you know impulse is a capital I. Force is a capital F. Time, lowercase t. Mass, lowercase m. Velocity, just lowercase v, but it's hard to tell sometimes. Momentum, lowercase m. No, jeez, Mr. Jern, what is wrong with you? Not lowercase m. I'm getting looking too far ahead here. Momentum, everybody knows it's lowercase p, especially a teacher. Change in velocity. All right, change in anything is going to be that delta, that Greek letter delta, and velocity is v. Change in momentum, there's that Greek letter delta. I could do that. In momentum, delta p. Wait, impulse variable. What if impulse variable is I? Then what is there is no variable for inertia. Because that is a fantastic question, and it's never really come up. There is no variable for inertia. Honestly, inertia is just completely and utterly represented by an object's inertial mass. Just if you think of the mass, that's the amount of inertia it has. All right, so we never mathematically or quantitatively looked at inertia. It's just that more mass means more inertia. That's it. Something that's 50 kilograms, it's gonna have twice as much inertia as something that is 25 kilograms. So that is a great question. We just use mass to represent inertia if we needed to do it quantitatively. All right, man, this is a great question actually. So and for the final, that won't come up because, like I said, we don't look at inertia quantitatively as numbers. But for this test, we're not even talking about inertia. We're talking about momentum and impulse. I mean, we could think of momentum as inertia in motion, because momentum, P is equal to mass times velocity. So the mass would be representative of the inertia, but there is no actual variable to represent inertia. Not at least in this class. So keep them coming. Keep them coming. I'm going to keep going as well until I see something. Okay. You throw a ball with 400 newtons of force for 0.2 seconds. How much impulse did you apply? How much momentum did it gain? Okay. Well, you look at the equation sheet, and impulse, hopefully this is pretty straightforward to you. You've been doing this, right? So impulse, as you hopefully well know, but if not, it's pretty straightforward, is force times time. It's the second equation on that equation sheet for impulse and momentum. You literally multiply those two together. So 400 newtons times 0.2 seconds. And you would think I could do, oh, it's 80. I've already done it. So 80 Newton seconds. And there you go. How much momentum did it gain? Well, once again, you're not sure. You're like, all right, well, impulse, and you really don't have a lot to go on. So you got that whole like string of I equals delta P. This one, right in the center. This one, holy cow. This one, and where is my? There we go. That's my pointer. And so it's asking about inertia. How much momentum did it gain? That's a change in momentum. Well, you could go either way. Go, well, the change in momentum is equal to impulse, or, because it's both the same thing, it's equal to force times time. So if you want to just recalculate it again by multiplying, you can do that. So it doesn't, but I'm not going to do that because I've already done it. So how much momentum did it gain? Why do I have a little, oh, there we go. Okay, I didn't want to like click. So the answer is how much momentum did it gain? I mean, you could just, well, I wouldn't put the plus. I was thinking positive, but I guess technically it is a positive, but it's equal to 80. Now this is a little tricky, and I know it's been throwing some of you guys off, but you can use the Newton seconds is okay, but if you want to use the units for momentum here, it would be fine. And wait, okay, hang on, I'll finish this, then I'll answer that question. And it totally relates because a Newton is a kilogram meter per second squared. And so if you multiply that by seconds, which you're doing right here, then that squared cancels out and you're left with kilogram meters per second, which is the same exact thing. So that's just a little aside. Technically, Newton seconds and kilogram meters per second are the same exact unit. It's just describing it separate a little bit differently. Okay, wait, if impulse only stops momentum, then wouldn't throwing a ball only have to do with momentum and not impulse? Throwing a ball, okay, everyday language, we say throwing a ball. I'm throwing a ball. And we leave it at that. Everybody knows what that means. In physics, we say, but what does that really mean? How can I quantify that? How could I change throwing a ball into something mathematical so that I can understand it better? I could make predictions and I could model it. I could make, whatever. I could simulate it and I could just basically put it in a calculator and describe it mathematically. So there's a few ways to do that. And the way we're looking at it right now is instead of saying I throw a ball, you could say I apply an impulse, because an act of throwing a ball is applying a force for a certain amount of time. So that's what physics is all about. We take just stuff that we do and can we understand it mathematically? So impulse only stops momentum. No, so what we've noticed by doing that is when you catch a ball, we say catch a ball, in everyday language. Everybody knows what it means to catch a ball. Physicists go like this. They say, what does it mean to catch a ball? Well, hey, it looks like you're applying a force for a certain amount of time. That's the same thing as throwing a ball, except it's reverse. And so we say you apply an impulse. You could say a positive impulse if you want. We apply an impulse to get the ball going. Now the ball has momentum as it flies through the air. And it has exactly the same amount of momentum as the impulse that you applied to it. Okay, so you throw hard, you follow through, you apply more impulse, the ball goes faster, it has more momentum. You don't throw very hard, or you chuck the ball, you just kind of like one of these, the ball doesn't have as much, you didn't apply as much impulse, so now the ball doesn't have much momentum, it doesn't go very fast or very far. Then, when somebody goes to catch the ball, they got to undo all that, okay? And so they have to apply another impulse, but in the opposite direction, so they apply a force over a period of time. And if they try to apply a lot of force and they just kind of stiff arm the ball might just bounce off because now the forces are too high because they didn't like cradle it in. They didn't apply it for a lot of time. So if they don't like catch it correctly, there's not enough time for it to slow down. And so I'm getting deep into the weeds here. Bottom line is impulse and momentum are very much related. An impulse causes a change in momentum. You throw the ball by applying an impulse. The ball now has momentum. You catch a ball by applying an impulse, and you take that momentum away. All right. Great question. Great question. I hope I answered it. Okay. Speaking of which, a 15 kilogram ball slows down from 10 to 5 meters per second. How much did its momentum change? So I'm just going to look at my equation sheet. Momentum change is this, change in momentum, right? And there's a couple options we can do based on our equation sheet. We've got two velocities and we've got a mass. So this is mass. These are two velocities, and we could say, well, this is our initial velocity, this is our final velocity, and those aren't really on the equation sheet, except if we take VF minus VI, we get the change in velocity. So V, that looks like a bad F, but it's an F. So if we take VF minus VI, we get our change in velocity. And so these two together give us our change in velocity. And so if we look at our equation sheet, the big clue, the easy one, was the mass. And there's really only one part of the equation that deals with that, and that's going to be this one, mass times the change in velocity. So this mass and this mass, the 15 kilograms, that's your big clue that you're going to have to do something like that. I mean, if you look at it, let me just pull that up again, maybe. There's only, I mean, this is it. This is the only thing that involves the mass. I mean, you could go over here, but I mean, it's asking for the change in velocity, momentum, not the momentum. So change in momentum is mass times the change in velocity. There's no other equation, part of the equation that involves mass except for that. So, excuse me. So, how much does it change? Well, the mass is 15 kilograms. The change in velocity, well, you don't necessarily have to do this part. But I mean, you can see it goes from 10 down to 5. And so again, go kind of, think this through a little bit. That is a change of negative 5 meters per second. My M's are terrible. And that could be verified because VF is 5, VI is 10, the initial velocity. And so 5 minus 10 is negative 5. And so the answer here is a negative 75 kilogram meters per second. Okay, I guess since it's an equation, I should put a box around that. That is the answer. That's how much the momentum changed. Bonus question, how much impulse was required to stop that ball? Whether that impulse was applied by somebody or if it was applied just by friction, doesn't really matter. It doesn't say. I don't care. I just, if I were to ask how much impulse that was, well, that's impulse. It's all the same thing, which means that how much impulse, it's going to be negative 75, and you could use kilogram meters per second. That's okay. It's slightly, just, it's not incorrect. It's just not appropriate. It's just not the word you would use. And you might just change it to Newton seconds. So, but I didn't ask that. So, but it all relates. I'm trying to remind you to think of these things in terms of the equations. All right, question 16 from the review guide. Speaking of which, so I had questions about this one because there's a lot going on. There's a lot of numbers here. And it says a 1,700 kilogram car is traveling at 20 meters per second. The driver presses the accelerator so that the engine provides 425 newtons of force for 20 seconds, causing the car to speed up. What is the final velocity of the car? And I look at the equation sheet for impulsive momentum. There is no final velocity mentioned there, except for what I just got done talking about. But I'm getting a little ahead of myself. Let's see how far we can get. This is mass. It's traveling at 20 meters a second. All right. So that's a velocity. It is a velocity, not a question mark, but that is its initial velocity, how fast it was going. 425 newtons, that's a force. 20 seconds, that's a time. And we want to know final velocity. So that would be VF. All right, so whenever final velocity is asked, you might want to start thinking, what's the initial velocity? Just say, okay, what is VI? Ask this. Ask, what is VI? Whenever you see final velocity, ask yourself, okay, maybe I need to know what VI is. That's how I knew that this up here was going to be VI. Plus, that's just how it started. Okay, I'm over-explaining. I tend to do that. I apologize. So I've got mass, VI, VF, I've got force, and I've got time. So looking at my equation sheet, I could pick and choose any of the variables in the equations in that string of 4. And I say, all right, M delta V is equal to FT. All right, I just looked at my equation sheet, and where did I get that from? I kind of did it backwards for no reason at all, but right, so I've got, it doesn't matter what order I did it in, but I just, in my brain, I just did it backwards. M delta V is equal to FT. So this, basically this equation right there, that equality, okay? So that's all I'm gonna do, okay? So mass is pretty straightforward, 1,700 kilograms. Delta V, the change in velocity, is, it's always VF minus VI. So here, let's do this up here. The change in anything is the final minus the initial. So the final minus the initial. So the final velocity, I don't even know. The initial velocity is 20. It's supposed to be an M. Equals the force, 425 newtons, times the time, 20 seconds. Now I just went ahead and plugged in my variables. I didn't even rearrange the equation ahead of time. I could totally have done that. In fact, I'm going to kind of make this a little easier. I'm not going to distribute the 1,700 kilograms. I don't need that in my life right now. What I'm going to do is I'm going to see about switching colors just to make this a little bit more clear. And maybe, there we go. And I'm going to just try to get, you do your algebra how you do your algebra. All right, I'm just going to get that out of there. I don't want that. I don't want to distribute that. I don't feel like I need to distribute that. And so I did that. And then what I'm going to do is I'm going to have VF minus 20. And so I want to get VF by itself. So then I'm going to add 20 meters per second to both sides. So plus 20 meters per second. Again, I'm doing algebra, so if you need me to further explain this, I can. So what's going to end up happening is VF is equal to 420. Why is it VF? Great question, and I'll answer that in a second as soon as I finish this up. 425 times 20 divided by 1,700. I got 5. So let's see, that's 5. So it's weird Newton seconds per kilogram plus 20 meters per second. And what ends up happening, because of what a Newton is a kilogram meter per second, everything cancels out. This is supposed to be a 20. Everything cancels out, and over here you're basically left with a meters per second. And so basically the answer is 25 meters per second. Okay. So another way I could have done that is, instead of plugging in all my numbers, I could have said mass times the change in velocity, VF minus VI, is equal to force times time. And then I just could have done the algebra from there and solved for VF before I plugged in all my numbers. Whatever works for you. All right. The question is, why is it VF minus VI, not VF? Okay. Because it's asking for the change in something. And whenever you ask for the change in something, it's always, what do you have now minus what did you have? So that's just how it goes. If I give you $20 and you had $5, no, let me phrase that. If you now have $25 and you used to have $20, what was the change? Well, what was the change in money that you had? What was the change in dollars? And so you would have to take the final money that you have, the $25, minus your initial $5. And so you increased by $20. All right, that's just the nature of the change in something. You always take what you have now, the final, minus what you started with. All right, just if you, like I said, think about it in terms of money or speed. If you're going 100 and you were going 80, how much did you change? Well, you went from 80 to 100, so you take final speed 100 minus the initial speed 80. You get a 20. You increased by 20. If you were going, that's the basic. That's just how you find change. Final minus initial. It's a very good question, but just think it through a little bit. And if you're not sure, if you get all, like, sometimes you sit down and take a test and your brain just goes, nope, we're not thinking anymore. Then just call me over during the test and I can help you out and remind you of that. I'm looking on the equation sheet. I don't think it's mentioned anywhere on there, final minus initial, but so I don't see it anywhere. So if you're not sure on that, just let me know. All right. Great question though. All right. An acceleration occurs every time there is an impulse. Let's see if I might. No, I'm not going to do that right now. Every time there is an impulse, there's going to be an acceleration. You don't have to put it in there if you don't want to, but just think about it. They say, and I don't know who they is, but generally it's good test-taking strategy that if you see the word always or every time or whatever like that, a red flag should pop up. But that's it. It's a red flag. Look at it carefully, okay? And you should say no, or at least that should be your default, if you're not sure, I guess. But it's only a red flag, because sometimes when you see the word every time or the always or always, whatever, you see that red flag pop up, it's just a red flag. It just means you should look closer at it, all right? An acceleration occurs every time there is an impulse. Well, what is an impulse? An impulse is a force times a time. The key right there is that force. And if you remember, F equals ma. If there is a force, there is an acceleration. So this one would be true. I don't know if I asked that on the equation or on the review guide, but that's just, again, something to keep in mind. All right, an acceleration occurs every time there's an impulse. True. Choice C is because I feel like that question came out of left field, but probably, and it did. But just, it's to reiterate the fact that what an impulse is. An impulse is a force times a time. What does C-er mean? That does mean, it just means, yeah, it's not a real choice. It's because true and false was not enough. I needed another one. Yeah. All right. I feel like we're getting to the end of this first part of the unit. Which experiences a greater impulse? A car pushed with 2,000 newtons of force for 10 seconds, or a truck pushed with 5,000 newtons of force for 4 seconds? Ooh. I don't know if you need a calculator. You might be able to do this in your head. You probably could. Just remember, impulse is force times time. So the car, I'm not going to write it out. 2,000, the truck because of more mass. Ooh, all right. However, it's not asking about, just be careful what it's asking about. It's asking about impulse. Okay. That would be my gut instinct, is to say the truck because it has more mass, just like you said. But it's asking about impulse. Okay. So let the equation guide your thinking here. Force times mass, right? So the car is 2,000, force times mass. It's force times time, 2,000 times 10. So that is what, 20,000 Newton seconds. The truck is 5,000 times 4. Also 20,000 Newton seconds. Okay, so the answer is they're the same. You notice that it doesn't even give you the mass. I've seen some really puny trucks, and I've seen some really big cars. It's a safe assumption that a truck weighs more and has more mass than the car, but it's not always the case. It didn't even tell us the mass of the car or the truck. It just told us what we needed to know: force and time. Make sure you answer the question that's actually being asked, not the question that you think it's asking, or the one where your brain immediately goes to. Great, and keep your answers coming, because it's important that I know where you're at. Okay. At one stoplight, the driver takes 10 seconds to accelerate to 40 miles an hour. At the next stoplight, the driver takes only 2 seconds to accelerate the same speed. How much more force will you feel at the second light? So you're increasing to 40. You're at a stop. The car stopped, and the car gets up to 40 miles an hour. At the first stoplight, the driver takes 10 seconds. At the second stoplight, the driver takes 2 seconds. Now, you see the choices. Like, wait a minute. Okay. Either way, because the car ends up going at 40 miles an hour, it has the same change in momentum. The car's mass, with everybody inside of it, doesn't change. The car's speed, when it gets to the 40 miles an hour, is the same. So the change in momentum is the same. What's different? The impulse is different. The combination of force and time together is the same. But because the time is going to be different, the force is going to be different. So because they took 5 times as long the first time, let's look at the other way. By taking only 2 seconds, that is 5 times less time, which means you're going to feel 5 times more force. Okay. So a couple things. Either way, it gets up to 40 miles an hour. The same car, the same speed. So momentum is mass times velocity. The momentum is the same. Same mass, same speed. What causes that momentum is the impulse, the change in momentum. Force time. Remember, use the equation sheet. Use the equation sheet to guide your thinking here. What are we talking about? It's asking about force, right? It's asking about force. So what in this equation sheet, where'd it go, is going to tell you about force? Well, this it doesn't mention anything about impulse in the question, so that's kind of useless right there. The thing that talks about force is right there. And the thing you know is that the mass and the velocity, the change in velocity is the same. It's still going from 0 to 40 miles an hour. So the change in velocity is the same. The mass is the same. Therefore, the combination of force times time is going to be the same, because that's algebra. And so since the combination is the same, because the time decreased 5 times, it's 5 times less time, that means you're going to have to feel 5 times more force in order to balance it out, because it has to equal the same. All right, come back to that one. You come back to that one. Or ask me questions. Ask me if you need to. All right, a small car hits a large truck. Whoa, hey, well, I'm reading the right question here. How does a cell phone case protect your phone if you drop it? I asked this one in class. Well, take a second and read them. It makes the phone take longer to stop, so there is less force. It slows down, so it doesn't hit as fast. It increases time and so it decreases the impulse. It is soft and absorbs the impact. Okay, right away there's that word absorbs. That's a red flag. Put that off to the side, because what does that mean? It's saying something that you want to hear, but it's not actually describing it. Okay, this may or may not be true, but that's not the physics behind it. So I'm going to just do that. How? It doesn't explain how. What does absorb mean? Well, okay, so absorb is like that, or that we don't want that word. Well, decreases the impulse. That's just not true. The impulse is going to be the same no matter what, force and time. So the impulse is going to be the same because the phone's going to change momentum, and the amount of momentum that it changes will be equal to the amount of impulse. So the impulse is going to be the same. That's not what decreases. It slows it down so it doesn't hit as fast. I mean, unless you have a parachute built into your cell phone case, that's not going to happen. It doesn't slow it down. Okay, it doesn't. That doesn't even make sense. Like I said, you need a parachute. It makes the phone take longer to stop, so it is less force. Yes, that is true. If you have to memorize like a little mantra for this, that's the thing. More time means less force. Just remember that. More time means less force. Even if you don't quite understand what it means or where that came from. Whoa, hello. That line doesn't need to be there. More time means less force. Just remember that. So if you say it takes longer to stop, that's more time, so there's less force. Just remember that. All right, small car hits a large truck. Which of these is true? The impulse felt by the car would be greater than that felt by the truck. The impulse felt by the truck would be greater than that felt by the car. The impulse will be the same for the truck and the car. The impulses will be different, but depends on how fast each vehicle is going. All right, I'm just going to go ahead and you might have some ideas here, but you got to think about this. Why am I asking this question? It's not going to be the gut instinct, the one that you think is obviously the right answer, okay? This goes back to Newton's third law. Newton's third law. For every force, for every action force, there's an equal and opposite reaction force. That means that the force is the same for both. The force experienced by both of them are going to be the same because Newton's third law. Every action, there's an equal and opposite reaction. Okay. Well, guess what else is the same? The time it takes is also the same because they're both in the accident for exactly the same amount. If one ends, then the other one ended. So if the force and the time are both the same, well, impulse is force times time, and they're both the same. That means that it's going to be the same. It is not be because cars are playing. Yes. However, the truck is also applying the same impulse to the car. They apply the same impulse to each other. Okay? And like I was saying, let the equation guide your thinking on this. Impulse, what? So you see, okay, the question is obviously asking about impulse. What the heck is impulse? Impulse is not a word we use a lot, right? So go back to the equation and refresh yourself, remind yourself, tell yourself while you're looking at a question like this, impulse is force times time. I don't know what impulse is because that's not a word we use. And so I'm just gonna say, all right, impulse is force and time. What do I know about the force? What do I know about the time? The time is pretty obvious. The time is gonna be the same because that's the time it takes for the accident for both of them. Once it's over for one of the cars, it's over for the other one, or truck, or whatever. The force, okay, Newton's third law for every equal, okay, it's equal and opposite, so the force is, you know what I mean? So go back to the equation. I'm looking for questions. All right. Notice I'm spending a lot of time on 4.1 because 4.2 is pretty straightforward. You guys, I think, are pretty good at that. The car is pushed with 500 newtons of force for 5 seconds, causing it to speed up from 5 to 9 meters per second. If that equation is true, and it is, what is the mass of the car? All right, this is a straight up algebra question. What is the mass of the car? You could only dream you get a question that this is this straightforward. You got to solve for mass. All right, so I need to I shouldn't have drawn a line there, but I'm going to divide. I'm going to, here, you know what? So Ft equals m delta v. I got to solve for mass. Okay, I'm going to divide both sides by delta v. Cancel that out. And so mass is force times time divided by the change in velocity. Now we did got to be careful here because of what we were talking about earlier. It goes from 5 to 9, up to 9. Okay, you don't have to plug it into the equation, and you could just imagine, okay, that means it increases by 4. Okay. Close. You missed something, you missed something. I'm not sure what though. So it went from 5 to 9. That is a change of plus 4 meters per second. So change in velocity, holy cow, let's just do this in the right order. Change in velocity is a positive 4 meters per second. And you could either just subtract 9 minus 5 because VF minus VI, or just go, it goes from 5 to 9. So that means that the force 500 kilograms. Hang on though. Remember, let the equations guide your thinking. The time is 5 seconds. The change in velocity is 4 meters per second. So 500 times 5. Let's just plug this in, times 5. Let's do it the right way. 500 times 5 divided by 4 gives me 625. Equals 625. Now, the units seem to be a hot mess. The seconds cancel out. There is a newtons. There's like a whole mess of things in here. We're just gonna, it's kilograms because it's mass. I'm not gonna spend time doing the units there like on the live stream. Okay, so you use the equation. Use the equation. You got it. You're getting it. You're gonna get it. Okay, one last question for 4.1. All right, a 2 kilogram blob of slime is thrown at 5 meters per second and sticks to the wall. A 2 kilogram ball is thrown at 5 meters per second and bounces back to you. Which one experiences a greater impulse by the wall? Okay, so a blob of slime and sticks, same mass. So we got the blob of slime and we got a wall. Pff, that's a horrible wall, but it's thrown and then it just sticks to the wall. A ball is thrown against the wall and it bounces back to you. Okay, so both of these is 5 meters per second. They're both 2 kilograms. And so they both have the same momentum, but which one experiences the greater impulse by the wall? Well, the gut instinct, I think, answer is that they're going to be the same, but that's not true. Because you might say, well, the numbers are the same. 5 times 2, that's 10. Both of them have 10. What does that mean? Okay, well, think about it this way. Yes, they both have the same momentum. But for the blob, it just lost 10 kilogram meters per second of momentum. The ball, when it hit the wall, lost 10 kilogram meters per second. But then it went back in the other direction. So it's going to be, because it's going in the opposite direction now, that's a negative velocity. So it's going to be going more. It's going to be like, it's going to lose even more momentum. It requires a much bigger change in momentum. And so the ball is going to require a greater impulse. Okay, the slime just lost 10. The ball lost 10, and then more was required, more impulse was required to bounce it back. Okay, so the wall, if it just stops the blob, it requires a certain amount of impulse. If it stops it and then returns it, that's going to be even more impulse. All right, I asked a question like this the other day. A motion cart moving at 10 meters per second collides with and sticks to an identical motion cart that is at rest. How fast do they move after they stick together? Do you remember? I hope there's no questions coming through on Remind. And it does tend to log me off, so I did double check just before I started this. I'm still logged in. Buckaroo Banzai is asking all the good questions here. All right, I don't know if you could see this, but right there, that's that graph. And we did that in class. So that green cart back here has a certain amount of speed. The yellow cart is at rest. And so when they collide, it's going to be, green is not the answer. The answer is it just doubled its mass, essentially. And so it has half the speed. Okay, they move at half the speed. Couple more slides, Double the mass. Here, look. Here, blah, 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 blah. Yeah. B because, yeah. Ooh, okay. Total, okay. You are you're correct. The because is correct, but not the answer. Now let me explain this a little bit better. And I'm glad you said that, because I was going to move on, and I just remembered that this is like, you got to remember that the total momentum does stay the same, but we're talking the total momentum. This yellow car was at rest, which means it has a momentum of 0. The green car has all the momentum, but it only has half the mass. Of the two cars together, the green car has only half the mass and has all the speed. And so now it basically has to have, now when they're together, the mass, there's more mass, but okay, let me explain this mathematically. The momentum stays the same. Okay, so the momentum stays the same before the collision and after collision. And so if you double the mass, the velocity has to decrease equally, all right? Because momentum stays the same. Okay, and you can kind of see it in this graph down here. I kind of covered it with my own writing. But if you look at this graph over here, you could see the total velocity is only half the story. As soon as the mass doubles, the velocity is cut in half. Okay. I mean, hopefully that makes some common sense too. I mean, if you're pushing something, if you're running and so, how do I put this? It can't go the same speed because now there's twice as much stuff. Okay. I don't know if that helped. There's a deeper explanation, but I think it'd be more confusing if I tried to go into that. But I can if you need me to tomorrow. So a ball is going 10 meters per second and it stops after bouncing off another ball that has twice the mass. How fast will the second ball go? So if I were to draw a picture of that, here's your first ball. It's got, and then here's your second ball. It's got twice the mass. So this one is going 10 meters per second. And then it bounces off of this one, it hits that one. And so now this first ball is stopped, and we got our second ball moving. What is its velocity? So this has just the mass, this has twice the mass. What do you think? So if we have twice the mass, what's going to be? Twice the mass. The total momentum is, so the total momentum is going to stay the same. This thing is starting out at v is 0, and now this one is v is 0. So if we now have twice the mass, what does that mean about the velocity? Well, purple, no. Who said purple? Nobody said purple. I like to think that people say purple because these jokes make me laugh, even though they're not really funny, but I still laugh. All right, the answer is C, 5, because you now have twice the mass, so you're gonna have half the speed. Second to last one. 100 kilogram object loses 10 kilogram meters per second of momentum during a collision with a 50 kilogram object that was at rest. How fast does the 50 kilogram object move after the collision? There's a lot of numbers. Okay. So what I would suggest is whenever you see a before and after, is do that chart before, after. I'm going to do a really horrible version of it. See, I can't even draw my line straight. So yeah, thanks. All right. a 10, okay. A 10 kilogram, okay. So loses momentum, okay. The rest. How fast does, okay, you know what? We don't even need that. We don't even need the chart. Because if we think about it, then if the object loses 10 kilogram meters per second, that means the other object has to gain it. So you know what? Forget the chart, because we're overcomplicating things, because that's what we do because we're honor students. We're like, whoa, we got numbers. We should do a chart. Okay, hang on. The chart might not be helpful. In fact, it doesn't help. Let's just think it through. An object loses 10. That means the other object has to gain 10. Okay. Momentum is mass times velocity. So if the second object now has 10 kilogram meters per second of momentum because it gained it from the first one, okay? So we got this gigantic thing coming and it bounces into this 50 kilogram thing. So they collided. This thing now has like a little like thing that pops up over it, like a little number that says plus 10, okay? Because it like this one loses 10, so it's like minus 10, and it's like plus 10. I don't know why I like think of life as like a video game sometimes, but basically it's like a little, I can just picture like a little green plus 10 and a little red minus 10 for the other one. So the plus 10, that means that it now has 10 more momentum, right? So how fast does it move? It was at rest, by the way. It was at rest, which means that it has 0 momentum. So now it has 10 momentum, 10 units of momentum, 10 kilogram meters per second of momentum. Okay, and momentum is mass times velocity. Okay, well, hey, wait a minute. It has how much mass? 50 kilograms? And we want to know its velocity? Well, okay, this turns into a simple algebra problem. I just divide both sides by 50 kilograms. 50 kilograms. And it turns out that it's going to be 0.2 meters per second is the velocity. Oh, well, multiple choice. There we go. Okay. So there will be a time and a place for those charts. I'm just going to say that not everything has to be a chart. All right. Don't overthink it. If you start to do a chart and it's not falling into place, like you look at this numbers and it's like, okay, I got to do the chart. Mass times velocity. Oh, wait, it doesn't tell me velocity. Oh, no. Like, don't freak out. That just means this isn't a chart problem. Okay. It was a little bit simpler than a chart problem. We lost 10 momentum. That means the other thing gained 10 momentum. Momentum is mass times velocity. It gives me the mass, and I got to figure out the velocity. Okay. Last question. A 5 kilogram ball is moving at 10 meters per second when it hits another ball and stops. Okay. You got the little animated GIF. The second ball was at rest. And now, so in the GIF, the red orange ball was at rest, and now it is moving at 8 meters per second. What is the mass of the second ball? Well, there's a couple ways we could do this one. Is this a chart question? I don't even know. Let's find out. So let's do before and after. Okay, just basic chart. So I'll just do the 5 kilogram ball. So 5 kilogram. It's moving at 10 meters per second. So the momentum is 50. Let's see, the other one is what, 8? No, wait, second ball is at rest. No, they're the same. They're both, And you gotta be careful with your numbers here. They're both pool balls, so they're both gonna be the same. Both cue balls, 5 kilograms. Although I don't think they weigh 5 kilograms. Rest. What is the? Oh no, we don't know the mass of the second. All right, read the question. Remember that part? I've been saying it. So mass times the velocity. Well, it was at rest. It doesn't really even matter. None of this mattered. It was all 0. So the total momentum is 50. All right, that means it's 50. And so the second ball, the first ball is now at rest. So that's 0. And basically something times 8 meters per second Okay, now it's moving. It has to equal 0. It has to equal 50. So 0 plus mass times 8 meters per second is equal to 50. All right. Well, don't worry about that 0. So mass times 8. So I'm just going to divide both sides by 8 meters per second. 8 meters per second. And that's going to cancel out. So the mass is whatever 50, 6.3 because kilograms. So you see how that, like, there's all those numbers swirling around, and that chart helped to separate the before and the after. And it helped me when I started going a little astray. I started to write when I was over here and I was like, well, they're both pool balls. And then I'm like, wait, no, it says, what is the mass of the second ball? I don't know it. And so by writing it down, it slows you down a little bit and gives you a chance to think about this stuff. Okay. Now, if it was like the previous question where I run into an issue like, hey, this isn't turning into a chart question, then I stop. I say, okay, what kind of a question is it? This one ended up working out as a chart question, and it wasn't quite the same as something. It was a elastic collision question, but it worked out. So take your time, do the chart, even if it's a really quick chart like I made. Okay, it's not as pretty as the ones on the practice, but the practice was the pretty ones to get you prepared for doing them on your own. And that slowed me down, and it helped me to process and think this through. Okay. So in summary, make sure you are able to do those practices, the charts. That was the closest thing I got to doing a chart question. You had like an entire packet of practice, which I think most of you guys did well with. Most people I saw when I was walking around were doing pretty okay with the charts. So I did put I linked my playlist. Now they're videos from 2015, so they're not quite as the quality I like anymore, but they still get the job done, and they should be helpful to you. Yeah. So I hope I answered the questions that you needed answered. I don't know if there were any. I think I answered some of these from the review guide here. Most momentum, yeah, just multiply mass times velocity. And then you could like do that for all of them. You could compare them. I did put the key to all this up on both the Google Classroom and the OneNote. Okay, so Mr. Jern, I got every single question wrong. Is that a battle planet? Okay, that you know what? You are not the only one. At least you're watching this. Okay, so you got every single that right there is a good thing, because I mean, it's not the best thing, but it's a good thing, because now at least you know what to look out for. So the battle plan would be probably it depends on how you want to. No, I know, I get it. It's not, it's very few people's forte. The battle plan would depend on your attack strategy here. You got a couple options. Definitely go back and check out the notes that's linked on the OneNote. Go back and look at the quiz that you may have taken. Look at the questions you got wrong. Look at the questions you got right on that quiz. Go back and look at the practices without the key. Maybe go open up a fresh version of it, of the practices, all the practices without the key, and see how well you could do to answer those, and then check the key. And then the biggest thing is, throughout all of that, like I said at the very beginning, and this applies to everybody, is use those equations to help guide your thinking. If you get stuck on a question, or you think you know the answer, those are even scarier when you're pretty sure of the answer and you know it. Just double check everything in terms of all these equations. Okay, what is momentum? Momentum is mass times velocity. What is impulse? Impulse is force times. We don't have a thing in our head about what impulse is. Okay, impulse is purely definitional. We only use it in physics, it seems like. So since we don't have a cultural understanding of what impulse is, go by what the equation is. All right, questions that ask you about impulse, make sure you go back, say, all right, I'm instead of saying impulse in my head, say force times time. All right, just think of it in terms that you do understand. Force and time, I think we do understand those. Look at the relationship. So that's what I would suggest, is just definitely like keeping those equations handy, and just ask questions when they come up. All right. And don't stress about it. We all get stuff wrong. And like I said, if you got everything right, that'd be amazing, but you might not need my class. You know what I mean? So anything else? All right. So we do have one more day in physics tomorrow in class. And I haven't 100% decided what we do. We'll probably play a review game, but we'll see. You can ask me questions, of course. Send me reminds. The test is on Tuesday. You have a whole day and a half to get to where you need to be. Okay, so you have the time. I realize it's not, my class is not your only class. So spend the time you need on all your classes, and then just use the resources you have. The OneNote, the videos, and the remind, and each other if you're comfortable talking to each other about this stuff. All right. Get some sleep. Don't stress. It'll be okay. Just study. Have a good one. See you tomorrow.